I'm making live streaming of this in YouTube, so
Yeah.
okay. Please switch off mute, okay? So good. So it's 7 o'clock, so shall we start?
We'll wait for a couple of minutes.
Couple of minutes. Okay.
Maybe due to the time difference, we'll give some 2 minutes.
Yes, sir. So, okay.
We have to discuss our summer training program Monday.
Cannot mute. Okay. I think we should start and
Yeah, we can start, I think.
yeah, yes, okay. Good evening, all. I welcome you all on behalf of CMPI for our monthly web lecture. Dr. T. Ganesh sir supposed to do moderation today's session, but due to some personal reason, he couldn't and convey his apology to all. I request that Dr. Vermugen sir to moderate today's session on behalf of sir. So, sir, please.
Yeah. Okay. Thank you, Dr. Bhatt. Good evening. Myself, Professor Velmurugan. I join on behalf of CMPI board. Welcome you all for the CMPI monthly web lecture series. Can you hear?
Yes.
Yeah, audible, sir. Audible.
Okay. Thank you for joining, taking time and joining this web lecture series. Today's lecture topic is Principles of MRI and its Applications for Practicing Medical Physicists. As we all know, MRI is a medical imaging technique mostly used in radiology and nuclear medicine in order to investigate and investigate the anatomy and physiology of body, and to detect pathologies including tumors, inflammation, and neurological conditions, etc. In addition to the above applications in radiology, magnetic resonance guided radiotherapy marks the beginning of new era. So this MR is a versatile and suitable imaging modality for radiotherapy, as it enables direct visualization of the tumor and the surrounding organs at risk. Moreover, this MR guided radiotherapy provides real-time imaging to characterize and eventually track anatomical motion. Nevertheless, the successful translation of new technologies into clinical practice remains challenging. Till date, the availability of MR Linac system is still limited. And also, this topic is a very vast and difficult to cover in one lecture. The focus of today's lecture will be much on the fundamentals of MR imaging and its applications. One announcement for the participants. Please feel free to drop your questions in the chat box. At the end of the lecture, speaker will be able to clarify your doubts, or you'll be able to answer your questions. Now let me introduce today's speaker. Today's speaker is Professor S. Panneer. After his post-graduation in MSc Medical Physics from Anna University, Chennai, he worked in various institutions like Nayyur International Cancer Center, Apollo Hospitals, and now currently working in Department of Radiology and Imaging, Sri Ramachandra Institute of Higher Education and Research, Chennai. He has many publications to his credit in peer-reviewed journals. He is a well-known teacher all over India, especially among radiologists and MD, DNB, FRCP exam candidates. And one thing, he has so far delivered more than 575 guest lectures so far. He has received 2 prestigious awards, namely Professor Kakarla Subbarau's and Dr. V.P. Narayanan's Lifetime Achievement Award. His area of interest is MRI, digital imaging, mammography, and is a member of a safety committee and NABH of SRMC institution. Much more we can tell about Professor Panneer. Due to time constraint, I stop with this. I present you Professor S. Panneer. Professor Panneer, sir, please.
Thank you, Dr. Velmurugan, for the wonderful introduction. I also would like to thank CMPI, in particularly Dr. Bhatt, for giving this wonderful opportunity to share a few ideas and information about the basic principle of MRI. You know that, as Velmurugan was mentioning, the imaging science or technology is going to play a vital role in radiotherapy planning. So that's the reason I thought we may not be able to cover everything, at least to some extent. I thought in the first lecture, let me cover about the principles of MRI, which is going to be the important aspect, and its applications also to some extent for the practicing medical physicist. With this introduction, let me go to the topic. The objective of my session today is to understand the basic principles of MRI and its importance in clinical application. The topics which I am planning to cover in 45 minutes to 50 minutes is a couple of slides about the history, types of magnets, few terminologies like spin, precision, radio waves, and resonance, and of course, the very important concept, what do you mean by T1 and T2? That is going to be the fundamentals of the whole MRI, and how this T1 and T2 plays a vital role in application, that is T1 weighted image and T2 weighted image and proton density image. Then I would like to highlight a few clinical applications of MRI. I also thought, let me also touch about the MRI has various advancements What are the recent advancements in MRI? Maybe a few slides about that. So that is going to be my game plan for today. With this, let me start with what is MRI? I think most of you might be knowing the basics because the audience is full of physics background people. Even then, I thought there are few terminologies, fundamentals I would like to brush up so that the continuity of today's session will be easier for me. So what is magnetic resonance imaging, MRI? It is a modality. Modality means it's a division to image the body without using radiation, X-rays. We should never forget the people who have worked behind this. We enjoy the MRI, but the struggle, what these people have had long time back, we have to remember at least. The left-hand side whom you are seeing is the Swiss physicist. His name is Bloch, and he is American physicist. His name is Purcell. Discovered in 1946 independently the principle called as NMR, Nuclear Magnetic Resonance Principle. And of course, that was extensively used in the physics and the chemistry lab in those days for spectroscopic studies. They are the Nobel Prize winners for physics. The first imaging technique, what I told previously, it's only a research-oriented one, but the first imaging technique, how it came. He is the American chemist. His name is Paul Latrobe, and he is Sir Peter Mansfield, an English physicist. In 1972, he produced a two-dimensional image of a proton in a water sample. They have taken a water sample, and you know that in water, it is hydrogen is the majority of component. It has a proton in the nucleus, one proton. So he has tried to image that proton in a water sample. That's how it started actually in 1972. Quite interestingly, an American medical practitioner, clinician, he is the inventor of first MR scanning machine. His name is Dr. Raymond Wagon Damadian. He started his own company called as Phonar Company. Fortunately, I also had an opportunity to see one of the equipment of this company, resistive magnet, which was installed long back in 89-90 in Nizam Institute, Hyderabad. Of course, it's not there now. It's an old technology, resistive type of magnet. So that's the history about MRI. Little bit only I have covered. Let me go straight away with the MR fundamentals. M stands for magnetic field. R stands for resonance. Of course, the radio frequency pulse plays a vital role in this area. I stands for imaging. In the bracket, I have mentioned relaxation. What do you mean by that? Can you see in the upper quadrant, you are mentioned a CT image. It's not totally white. It is not totally black. You see white structure, you see black structure, and in between gray shades. And this technically we call it as pattern of density. This pattern of density, what is the parameter responsible for that? If you see differential attenuation. So differential attenuation is the parameter responsible for this pattern of intensity of information. But when you come down in MRI also, you see white structure, black structure, in between gray shades. And what is the parameter responsible for that? It is differential relaxation. That's how the imaging comes. So in X-ray and CT, it is differential attenuation is the parameter. And in case of MRI, it is differential relaxation. With this introduction, what do you mean the MR instrumentation here is? Of course, there is a lot of devices or what you call the components are there in MRI. I'm not going to the detail because that itself is a separate topic as such. The major component what we use in MRI is a large magnet. Of course, radio waves is the another component. And of course, computer is used for processing the data. One point to be remembered here is the magnet what we use is large enough to surround the patient. It means that the bore of the magnet should be quite wide. Why I am mentioning this is initially it was 60 and then 65 centimeter. Now even 70 centimeter bore is available. Wide bore we call it. What is the advantage for radiotherapy planning and all? If you have a wide bore, it's good actually. But the problem is, if you have a wide bore, it is easy and good for us. But for the engineer, it is going to be a challenging task As the bore is going to be bigger and bigger, maintaining the homogeneity of the magnetic field inside the bore is going to be a tough job for the engineers. So there comes the limitation. At present, maximum 70 centimeter is the bore size available. So that's one point to be remembered. Now, coming to the M part of MRI, that is a magnet I told you. Magnet, the basic types are two, permanent and electromagnet. In electromagnet is sub-classified into resistive and superconducting magnets. Coming to the permanent magnet, few bullet points I would like to highlight. Permanent, as the English meaning says, always the field is going to be on. And the shape of the magnet looks like an horseshoe, so we call it as a horseshoe type magnet. And the magnetic field direction is going to be vertical there from ear to ear, vertical direction. Of course, there is no consumable ear, so low running cost. Since it is open, we also call this system as open MRI system. The field strength available 0.2 Tesla, 0.3, and maximum we can go up to 0.4 Tesla. So that's about the permanent magnet. Coming to the electromagnet, a small physics, all of you know that. If a charged particle is going to be stationary, you will have an electrical field around that. If the same charged particle is going to move at a constant speed, you will have a magnetic field also. Keeping this in mind, I have a coil. I'm going to give a current to the coil. What do you mean by current? Flow of electrons. Electron is a charged particle. If the charged particle is going to move, it is going to produce a magnetic field. Hence, it is called as electromagnet. Magnet produced due to the flow of electrons are called as electromagnet. Here, this is classified into two. One is a resistive magnet. What is resistive magnet? I have a coil. I give a current to the coil. Magnetic field is produced. I'm going to increase the current. Magnetic field also will increase. Further, I increase the current. Magnetic field also will increase. But I cannot increase the current as I like because there is a limitation by a parameter called as resistance in the coil. Resistance. Hence, the magnet thus produced a resistive magnet. And the maximum field strength, what you can achieve with this type is also 0.3 Tesla only. Above this, it's difficult. And of course, it is very complicated and cumbersome process to maintain this magnet also. To overcome this, a superconducting magnet have been introduced. What is that? Can you see the black color? This is the coil. It is immersed in a cryogen. Cryogen means extremely low temperature liquid. What we use is liquid helium, whose temperature is 4 Kelvin, that is minus 269 degrees Celsius. Imagine it is extremely cold condition. When I am going to immerse the coil inside this liquid helium, at this low temperature, absolutely there will be no resistance in the coil. This process is called as supercooling. Absolutely there is no resistance in the coil means I can pump the current as I like and I can increase the magnetic field strength as I like. Hence, the magnet thus supercooled and thus produced are called as superconducting magnet. The alloy, that is a coil which we use, is niobium and titanium alloy. With the help of this, I can achieve 0.5 Tesla, 1 Tesla, 1.5 Tesla, and 3 Tesla, and even now 7 Tesla are commercially available. So this is called a superconducting magnet. To put in a single sentence, the coil, when it is supercooled, the current can be increased and you can achieve whatever the strength you want. For example, approximately 500 amperes of current has to be given to achieve 1.5 Tesla. So that's about the superconducting magnet. But commercially speaking, permanent and superconducting both are available. Permanent, very minimal, maybe less than 5%. 95% are superconducting magnets are utilized for clinical purpose. One more point to be remembered here is, I told you the magnetic field direction in case of open MRI is vertical. But if you see the closed MRI, you see the patient goes inside like this. I would like to tell the orientation, which is very important and it is common for CT and MRI, and it will be useful for you in planning also. This is the cranial end of the magnet, caudal end of the magnet. This axis is called as Z axis, Z axis. Right, left. This is called as x-axis. Anterior, posterior, this is called as y-axis. So the longitudinal axis, that is the cranial caudal, this axis is called as z-axis, please remember. And here you see the magnetic field, north pole, this is the north pole of the magnet, this is the south pole, and you see the magnetic field direction here is horizontal. In open MRI it is vertical, in closed MRI it is horizontal. This is one difference between this and this. So that's about the basic types of magnet. To put as a summary, we have permanent, we have superconducting magnet, and unit of magnetic field strength is Tesla. And in case of permanent, less than 0.5, and here we have 1.5 and 3 Tesla at present in India commercially, and 7 Tesla in abroad it is available. That is about the M part. Now, before going into the next, I thought I'll discuss for 5 minutes about bunch of terminologies which we should be familiarized in understanding the concept of MRI. Scalar and vector, what do you mean by field, nuclear spin, precision, precisional frequency, radio frequency pulse, and finally resonance. By understanding all this terminology, we will be in a position to understand the climax of today's session, that is understanding what is relaxation. Let us go one by one. You know it, but still, I'll just go through quickly. Scalar and vector quantity, basically it is a physical quantity. If I'm going to say 20 meters per second, then I'm telling about the speed. If I'm going to tell 20 meters per second in the direction of east, in the direction of the west, if I'm going to add the direction, then it will become velocity, which is going to be a vector quantity. So physical quantity, we have scalar and vector. It means magnitude only. Vector means magnitude plus direction. That's one point to be remembered. Then second one is field. What do you mean by field? You have a bar magnet. In the surrounding, you see a dotted lines. It's a region in space. It's a region in space. When I keep some metallic object here, it will experience a force. No need that I have to bring metallic object and touch the magnet. When I enter this zone, it is going to be attracted. It means that it experiences a force that is called as field. And if it is going to be by magnet, we call it as a magnetic field. What is the unit of magnetic field? Tesla. Conventional unit, Gauss. What is the relation between them? 1 Tesla is equal to 10,000 Gauss. Quite interestingly, all of us should know that Earth itself has a magnetic field, which is 0.05 millitesla. For example, I'm going to have 1.5 Tesla in this room. Do you know what is the power of that? It is 30,000 times stronger than the Earth magnetic field. If I'm going to have a 3 Tesla magnet, it means 60,000 times roughly it is going to be stronger than the Earth magnetic field. Imagine how powerful it is going to be. That's only I always used to insist that always we talk about radiation safety. But similarly, very equally important is the magnetic safety also. Because any metal enter inside, it will act as a projectile. So we should be very careful. So that's about the magnetic field strength. From this slide, maybe a few more slides, I will be spinning your brains. First one is the nuclear spin. What do you mean by that? You know that if any object is going to move around its own axis, we call it as a spin. Earth move around its own axis, we call it as a spin. Similarly, in the human system basically made up of 80% of water. It is hydrogen and oxygen. Forgot about oxygen. Majority is hydrogen nucleus. Hydrogen, you know, atomic number is 1. If you take the hydrogen nucleus, 1 proton is going to be there, no neutrons. In nature, I think all of you know by quantum physics, in nature, in the basic phenomena here, this hydrogen nucleus has a natural phenomena of moving around its own axis. Since it's a positive charge particle, when it is going to produce move, it will produce magnetic field. So what happens? I am going to tell two statements now. Human body is made up of millions and millions of hydrogen nucleus. But now I am telling, since the hydrogen nucleus is going to move around its own axis, what is actually moving? Hydrogen nucleus. So we call it as nuclear spin. So when hydrogen nucleus is going to move, because it is a charge particle carrying positive charge, it will produce a magnetic field. So each hydrogen nucleus in the human body is going to behave as a tiny chota magnets. So to correct my statement now, what I'm going to say, the human system is made up of millions and millions of tiny chota magnets. So that is the message of this slide. Now, I'm going to take 5 hydrogen nucleus in the human system. You see, they are randomly oriented. The arrow indicates North Pole, tail indicates the South Pole. Is all are in same direction? No, they are oriented in different direction. But when I'm going to place the human system inside the strong MRI machine magnet, you see all the hydrogen nucleus are aligned parallelly to the main magnetic field, and few hydrogen nucleus who are having excess energy can align anti-parallel also. As per the basic fundamental, the parallel anti-parallel cancel each other, and the left out parallel itself is enough for imaging in MRI. We will forget about the anti-parallel now. We think that it is aligned parallelly to the main magnetic field direction. That is one message. Now another movement is precision. What do you mean by precision? Classical example, I'm going to put a spinning top. When you put a spinning top, you see there will be 2 motions will be there. The top will be moving around its own axis, that is called a spin. Apart from that, there is another motion where the nail at the bottom will be fixed in the ground and the head will be revolving in a circular fashion. That movement is called as precisional motion. Have a look here. The hydrogen nucleus similarly in the human system move around its own axis, that is spin. At the same that the tail of the vector is fixed and head will be revolving. This motion is called as precisional motion. How fast this is moving? This is called as precisional frequency, and this was found by Dr. Joseph Larmor. He has found a small equation. I am not going to the detail about that simple equation. Precisional frequency is proportional to the magnetic field strength. And of course, if you remove the constant, it is going what you call proportionality. Constant, it is gyromagnetic ratio. Here, message here, precisional frequency is going to be directly proportional to magnetic field strength. It means that if I'm going to place the human system in 1.5 Tesla and 3 Tesla, the precisional frequency of the hydrogen nucleus is not going to be same. What is the precisional frequency? If I'm going to keep in 1 Tesla, the precisional frequency is 42.6 megahertz. If I'm going to keep in 1.5 Tesla, it is 63.9 megahertz. If I'm going to keep in 3 Tesla, it is just double, 127 megahertz. So what is the message? Precisional frequency is directly proportional to magnetic field strength. For today's session, assume that I'm going to have 1.5 Tesla. So we'll remember this numerical value. That is 63.9 megahertz is the precisional frequency of the hydrogen nucleus in 1.5 Tesla. Next, radio frequency pulse. Of course, all of you know that basically it is an electromagnetic wave that results from the brief application of an alternating current. So that is called as RF pulse. Now, last terminology which you are going to see now, it's a resonance. All of you know the fundamental physics about resonance, but still for the younger people, if any students are there, maybe the younger physicists, this might be useful. What do you mean by resonance? I'll give an analogy for that. It's a long race. 2 drivers are going to go for a long race, blue driver and red color driver. On the long race in between, this driver feels hungry, but this driver have food. But when he asks the food, they both are traveling at different speed. This guy is going to throw the food to him. What is the probability that this guy can catch the food? Very, very minimal. It will fall down on because both are traveling at different speed. Instead of that, assume that both of them are going to travel at the same speed. Then what happened? Exchange of food is going to be very simple, isn't it? That's all. So resonance is nothing but if 2 objects has a similar frequency, exchange of energy takes place. If 2 of the friends are going to have a resonance, that is frequency matches, exchange of knowledge takes place. Similarly, here the exchange of energy takes place. So as I said, in 1.5 Tesla, the precisional frequency, what we have to remember for today's session is 63.9 megahertz. And also remember, this is only for hydrogen nucleus. Whatever I'm going to talk today or MR imaging means, it is only hydrogen proton imaging, not about any other thing. So now we have finished seeing the bunch of terminologies. Let us go to the climax of understanding what is T1 and T2. This one, instead of putting in one slide, I am going to put in steps actually, so that it will be easy for you to understand. 5 or 6 steps I am going to explain you. In the first step, what you are seeing here, a big pink color arrow. I have mentioned this end as North Pole, this is South Pole. This is the main magnetic field direction, that is MRI machine. I told you that cranial end is the North Pole, caudal end, foot end is the South Pole. So this is the cranial end and this is the caudal end, foot end. And I have given a name for this BZ. What is BZ? Vector. I told you, no, vector means magnitude direction. What is this craniocaudal direction? I told you Z direction. So I have given Z. What is B? That is the magnitude of the magnet. What is the magnitude? I told you it is 1.5 Tesla. So BZ vector means 1.5 Tesla in the direction of Z. That is the meaning of BZ. I hope you understand the first step. Let me go to the second step. Now what I am going to do is I am going to put the patient inside the MRI equipment. When I put the patient inside the MRI equipment, you see all the hydrogen nucleus in the human system will align parallelly to the main magnetic field. Here in this diagram, I have taken some 6 hydrogen nucleus shown in blue arrow. All are aligned parallelly to the main magnetic field. So this is the second step. Now I'm going to take one hydrogen nucleus for explanation purpose. Take one hydrogen nucleus. Can you see one small arrow? That arrow, I'm going to take this as one arrow, one hydrogen nucleus, and I'm going to give a name MZ for that vector. Why? Z? Yeah, same direction, so Z. What is M? That is the magnitude of that hydrogen nucleus. That is the magnet, tiny magnet. I am giving an arbitrary value, M. So that is called as MZ. Please listen carefully. This is in vertical direction, that is MZ. This is precessing at what frequency I told you? This is 1.5 Tesla. At what precisional frequency it is moving? 1.5 Tesla means it is 63.9 megahertz. So it is precessing at 63.9 megahertz. The problem is this tiny magnet is aligned parallelly to the main magnetic field. If I want to study about this, I may not able to study I will not be in a position to study about this because in front of the huge magnet, this is a chota magnet. So what I'm going to do, I'm going to change the orientation of this. How? For that, I need a external force or external energy. For that, I need a radio frequency pulse. I am going to apply radio frequency pulse. For example, 90 degree. When I apply 90 degree, that will change 90 degree. When I apply 30 degree, it will change 30 degree. When I apply 180 degree, it will change 180 degree. For easy understanding of today's session, I'm going to apply 90 degree RF pulse. When I apply 90 degree RF pulse, you see exactly what happened. It has come to the horizontal plane now. Now no more I can call this as MZ. Now the direction is different, MY. I'm going to name it as MY. Remember here, originally it is MZ. There is a vertical component. Horizontal, nothing is there. When I apply RF pulse, horizontal has become maximum and vertical is 0, minimum. Fine. Now what I'm going to do is I'm going to switch off the RF pulse. When I switch off the RF pulse, what will happen? It will try to go back to the original condition. For example, if you take a spring inside the ballpoint pen, compress it. When you remove the finger, what will happen? It will go back. That going back is called as relaxation. Similarly here, I applied RF and it has come down here. When I switch off the RF pulse, this vector will try to go back. What will happen? You see here, when I switch off the RF pulse, you see that vertical component MZ, which is 0, it is trying to regrow slowly till it attains the original value. Have a look here. Originally it is maximum. Apply RF, vertical is 0. When I switch it off, what happened? This vertical is 0. No, from here it is going to increase, isn't it? It will take some time to relax back. That time is called as relaxation time. That is T1 relaxation time. That is regrowth of vertical component from minimum to maximum is called as T1 recovery or T1 relaxation time. Simultaneously, one more thing happened. That is the horizontal component is My. When I switch off the RF pulse, the horizontal component My is going to decay. It is going to decrease till it become minimum, which is the original value. So the time taken for the horizontal component to decay from maximum to minimum That is called as T2 decay or T2 relaxation time. To put in a summary, the regrow of MZ component, that is vertical component from minimum to maximum, is T1 relaxation time, and the decay of horizontal component My from maximum to minimum, that is called as T2 relaxation time. One more point to remember. I told you the regrowth of vertical component MZ from minimum to maximum is T1 relaxation. But theoretically, what they say, no need that you have to wait 100% to regrow. When it reaches 63% of the original value, see here it is regrowing. When it reaches 63% of the original value, what is the duration it takes? That is called as T1 relaxation time. Then you can ask me, then how much time it will take to regrow fully 100%? That will take 5 times T1 value. How many times? 5 times T1 value. Similarly, the decay of the horizontal component, no need to wait till totally it decays. When it decays 63% and 37% is left out, 37% is left out, that duration is called as T2 relaxation time. Here also you can ask when it will decay 100%. That will also coincidentally will take 5 times the T2 value. So that is called as T2 relaxation time. I hope all of you got the message. Now you will have a doubt. Both are happening simultaneously. T1 is regrowing, T2 is decaying. Is T1 is equal to T2? Or T1 is greater than T2? Or T2 is greater than T1? Simple analogy. A person is climbing the mountain and same person is coming down. Who will take more time? Person climbing up going to take more time rather him, isn't it? Can you look into this? Don't see as a hill. See the cursor. It looks like a regrowth curve. This looks like a decay curve. So regrowing is always going to take more time. That's the message actually. So please remember the decay is going to be, sorry, one second. Always T1 is going to be greater than T2. Never forget it. It's a simple app. So why? You can ask why. Because it has so many reasons. One simple reason I'll tell you. Due to the magnetic field inhomogeneity, the decay process is going to be faster. Even though we say maintaining homogeneity inside the bore of the magnet, 100% homogeneity we cannot achieve. There will be mild inhomogeneity will be there, maybe less than 1%. So that is going to create the T2 relaxation to decay faster. I have a comparison here. I have mentioned T1 and T2 values, particularly for 1.5 Tesla. Different values I have given. For today's class, I'll take 3 tissue for you to understand. You know, in brain, you have white matter, gray matter, CSF. You see, white matter, 790 millisecond is the T1. So when I apply RF pulse, it is going to come horizontal. When I switch it off, it takes 790 millisecond to regrow to 63%. But what about the T2? It takes only 92%. Decay is going to be much rapid. Similarly, gray matter, 920. See the CSF, 2400 millisecond. You wait for a few more slides. I'm going to explain you how actually it looks in the image. So that's about the T1 and T2 values for 1.5 Tesla. Now, you know that energy can be neither created nor destroyed. I give energy to the patient in form of RF energy. So what I am going to get back from the patient, that is going to be called as signal. The RF pulse, once it is switched off, the signal which is going to be received from the patient is going to decrease rapidly. And that is going to be called as free induction decay, and the signal looks something like this. How I am going to collect the signal? With the help of different receiver coil. There are dedicated receiver coils are there to receive the signal for various areas of interest. For example, for brain, we have a brain coil. Extremities, we have a spine coil. We have a body wraparound. Body wraparound means when I want to do chest, abdomen, pelvis, I have a coil, dedicated coil. I'm not going to the detail. Maybe in the subsequently when I'm going to talk about MR instrumentation, we can go in detail. So this is the device which is used to collect the RF signal from the patient. Fine. So I have done important aspect of making you to understand what is T1 and T2. After that, I told you that I'm going to collect a signal. That one signal, that is after switching off the RF signal, I'm getting an RF signal from the patient, isn't it? That signal is called as echo. that one echo is not sufficient for me to produce a beautiful image on the monitor, MR image. So what I am supposed to do? I have to repeat the process. What do you mean by that? Apply the RF pulse, switch it off, collect the echo. You do it once again. Apply the RF pulse, switch it off, collect the echo. Like this, I have to continue. You may ask, how many times I have to do? That depends on the matrix size of the image. For example, I'm going to do 256 by 256 matrix. 256 times I have to do it. So what will happen? Apply 90 degree, switch off, echo. Apply 90 degree, switch off, echo. Like this, I'll be getting 256 echoes. Now you add up all the 256 echo, that is a beautiful MR image. That is called as pulse cycle. What do you mean by pulse cycle? What is cycle? Any process, if you are going to do in a periodic way, we call it as cycle. Here I am going to do periodically what? Applying the RF pulse. Hence we call it as pulse cycle. Here you are going to learn two parameters. The time gap between the first RF pulse and the second RF pulse is called as time for repetition or repetition time. Technically we call it as TR. When you see an MR image, when it comes for MR, what you call treatment planning, you'll be seeing all this parameter. If you know, it will be well and good for you so that you understand better. And the time gap between the 90 degree RF pulse and the collection of echo, it is called as time for echo or echo time, which we call it as TE. I'll repeat once again. Time between two RF pulse is called as repetition time, TR. Time between the RF pulse and the echo is called as echo time. We call it as TE. So what you have learned now? You have learned 4 parameters now. That is T1 and T2, relaxation. That refers to the tissue property, which you and me cannot change it, inherent property of the tissues. But TR and TE are the equipment parameters, which we can play around with the system. For example, you would have heard about in X-ray machine, they play around with KVP and MAS to get different images or different, according to the thickness of the patient, they vary. Here, similarly, we play around with TR and TE and we get different shot of an image. So this is the final information. T1 and T2 refers to the tissue property. TR and TE refers to the equipment parameters. Now we will come how this T1 and T2 applied. That is the application. We have a different types of images. We have T1 weighted image, T2 weighted image, proton density image. Why? See, the T1 relaxation of various tissue happens. T2 relaxation of various tissue happens simultaneously. Take 3 tissues for understanding: white matter, gray matter, CSF. The hydrogen nucleus in the white matter, gray matter, CSF, all are going to have T1 relaxation and all are going to have T2 relaxation. But I may not be able to collect both the information simultaneously. Can I eat and sleep? I cannot. Similarly, I can collect the T1 relaxation of various tissue, or I can collect the T2 relaxation of various hydrogen nucleus in various tissue. Any one is possible. If I am going to give priority to the T1 relaxation of various tissues, then it is T1 weighted image. If I am going to give priority to the T2 relaxation of the hydrogen nucleus in various tissue, then it is T2 weighted image. There is another option. I will not bother about T1 and T2 relaxation. I will be focusing on the density of the protons in different tissue. How much density of protons in white matter, gray matter, CSF. Based on that also I can produce image. That is called as proton density weighted image, basically. Let us go through one by one. To put in a summary, I want to do T1 weighted image. I have to use short TR and short TE. This is the parameter we use. When I want to do T2 weighted image, long TR and long TE. When I want to do PD, proton density, long TR and short TE, different combination. You may know, you may ask, what is short TR? What is long TR? What is short TE? What is long TE? Have a look here. Short TR means, you know what is TR, between 2 RF pulse. If the short TR, if I'm going to set in the system less than 600 milliseconds, it is short TR. Anything greater than 1800 or 2000 milliseconds, we call it as long TR. Short TE means less than 30 milliseconds. Long TE means greater than 80 or 90 milliseconds. When you use this combination, short TR and short TE, I'll be getting automatically T1 weighted image. Long TR and long TE will get T2 weighted image. And another combination, long TR and short TE, proton density weighted image. It is neither T1 nor T2. So that's how we get the different type of images. Now, have a look at the image. You see, this is the T1 weighted image. This is the T2 weighted image. For a physicist to understand simple way, I'll take three different tissues. Take this left-hand side image. I'll take three different tissues: white matter, gray matter, CSF. Here, the white matter appears white. Gray matter, this is all gray matter. This is appear gray. And CSF, cerebrospinal fluid, appear black. White matter appears white. Gray matter appears gray. CSF appears black. Correct? That's T1 weighted image. But you should not take granted. Why? Why it appears like this? For example, I'll take one tissue for you to understand how it appears like this. For example, take this one, CSF. How it appears? Black. In T2 weighted image, how it appears? Bright. So now I am going to give justification for you how it appears. See here, T1 weighted image is black. What is the CSF value you see here? 2400 millisecond. What is the value? 2400 millisecond. So the hydrogen nucleus in the CSF will take 2400 millisecond to come back to the original position. That is 63%. It will take 2400 millisecond. But what is T1 weighted image? Short TR, short TE. What is short TE? I am going to take 30 millisecond. So I am going to acquire this data in 30 millisecond. When I am going to acquire the data in 30 millisecond, will the hydrogen nucleus in the CSF would have regrown? Not at all, because this will take 2400 milliseconds to regrow. So in 30 milliseconds, it will not have regrown at all. So I will not get any signal. That's the reason it is hypo signal intensity. We call technically hypo signal intensity. You see white matter, gray matter. Have a look here. White matter, gray matter. White matter is 790. Gray matter is 920. Which is going to regrow faster? White matter. That is the reason white matter appears bright when compared to the gray matter. So that's how the signal intensity is going to appear in the image. Come to this right-hand side. Why here CSF appears bright? Because when compared to all the tissue, CSF, hydrogen nucleus in the CFS, has long T2 value. That is, it is going to decay slowly. When it is going to decay slowly, the left out component will be more. That is the meaning. So CSF, the left out component will be more. That is the reason when I'm going to acquire the data, since the hydrogen nucleus in the CSF, the left out component is going to be more, I'm able to see it as a bright. So that's how the signal intensity is going to be. Here, why the white matter is black and this is the gray? Because you see here, white matter is decaying faster than the gray matter. That is the reason white matter appears darker when compared to the gray. So that's how the signal intensity of various images in MR going to appear, and that's the way we interpret the image also. Okay. Now another image is the proton density image. This is neither T1 nor T2. How we say male, female, in between we have a transgender. Like that, it is neither male, neither female. It's in between. So we call it as neither T1 weighted nor neither T2, in between. That is called as balanced imaging or proton density image. For this, we use long TR and short T. So that's about the image information. But we also should understand why the short TR and short T give T1 weighted image. That is the next level of understanding. We should not assume that short TR, short T will give T1 weighted image. I'll rush through quickly. You have a look here. I have shorter T1 value, one tissue, longer T1 value, one tissue. As soon as I switch off the RF pulse, you see this is regrowing because shorter T1, so it is regrowing quickly. Longer T1, it is regrowing slowly. Okay. When I use a short TR, you see the difference between the two tissue, I'm able to appreciate better. But when I'm going to wait for long TR, both are going to merge. I may not be able to see the difference. That is the reason I'm using short TR, so that I'll have good contrast here. Why I'm using short TE? TE actually reflects on the decay curve. You see, this is the short TE, the tissue decaying faster, that is T2. This is decaying little slower. Short TE means the T2 difference is less, but T2 difference is more when I use short TE. So when I use a long TE, the T2 effect will come on the image. I don't want the T2 effect because I am doing T1 weighted image. When I use a short TE, the T2 is merged, so I don't have the effect on T2. That is the reason short TER and short TE I use, because short TER, in order not to eliminate the effect of T1, I have the effect of T1. Short TE, because it is merged, that is the T2 curve, it is merged. So I will eliminate the effect of T2. I don't want T2. So that is about T1 weighted image. What about T2 weighted image? Long TR, long T. Why I use long TR? Because when I use long TR, this gets merged. So T1 effect will not be there. When I use long TE, you see good difference, T2 effect. I want that. That is the reason I use long TR and short TE. The third one is the proton density, where what I use long TR, short TE. When I use long TR, it merged, T1 effect lost. When I use short TE, it is merged, T2 effect lost. Then what is left out? Density of the proton. So that's how the image weighting is done in MRI. So what is the take-home message at present? I have 5 more minutes to talk. What is the take-home message? We have learned what is T1 and T2, and we also learned what is TR and TE equipment parameter. Using all this 4, we are able to get the T1 weighted image, T2 weighted image, and proton density weighted image. This is the application aspect. Coming to a little bit of clinical application, this is the brain imaging, what you see here. Wonderful soft tissue differentiation are well appreciated. For example, a layman itself can see this image and say, some laddu is there, some tumor is there. That sort of an understanding. See, actually, we used to teach anatomy with the help of textbook. As if we used to say that we can teach MRI with the help of MR images. Such a beautiful white matter, gray matter, CSF, bone, skull bone. Outer periphery, you see bright, that is the subcutaneous fat. That sort of an anatomical, see here, this is corpus callosum. You see the brain stem. What else you want? All the anatomy, we can read it. This is the spine imaging, wonderful. You see, this is a vertebra, this is a vertebra. In between this, we have an intervertebral disc. This is the normal disc up here. This is the T2 weighted image, normal disc up here. Can you see? Bright, hyper intense signal. But what happens as the age process goes above 60 or 65, you see the disc has become degenerative changes. So it has become black, no fluid content, no water content, no hydrogen content, no signal. So you have a hyposignal intensity. Here you see this comes out and this black line is the nerves. So this is called as disc prolapse. It comes and hits the nerve and patient will have a severe back pain. So this sort of a soft tissue appreciation can be possible only with the MR. And similarly, you want to see the bone metastasis is wonderful. Of course, we do a bone scan or PET CT also. And if you want to do the characterization here also, we can do it with the help of MR imaging. And see how beautifully this is the MRCP means it is something we are going to study about the gallbladder, basically, what you call the digestive area. This is the gallbladder, what you see here. And we are able to see the cystic duct, everything. But what you see here is gallbladder totally consists of bile. Bile means more hydrogen nucleus will be there. It will be bright like signal. But only this portion appear bright. This is totally not seen, hypoid signal. Why? This is full of gallstones actually. So that sort of information we get. Of course, we also can do a whole body scan in MR also. And in MR pelvis, of course, these are the images which is sent for radiotherapy department for planning. You know that here they mark the GTV as well as the CTV. And you see here the lymph nodes, what you see. You should know why, what is this? The doctor will say, this is the lymph node. We should be able to appreciate, it's a hypointense signal. Correct, the lymph. But what happens at the same time, I want to explain one more thing. See, if you find a lesion in the brain, something like this, they give the contrast and they see enhanced lesion. So for treatment planning, it's going to be much more useful. What do you mean by enhancement? We give a contrast here. Here the contrast, what we give is the gadolinium contrast base, gadolinium based contrast. What actually that gadolinium does is, as soon as the contrast enters, it reduces the T1 relaxation time. So what happened when it reduces the T1 relaxation means it regrows quicker. When it regrows quicker means I'm going to get more signal. That is called as enhancement. You see before the contrast, post contrast, you see the lesion better. The visualization of enhancement is going to be better. So which is going to be useful for us in the planning. So similarly, this image also. Okay, that's about the contrast. The last few slides, I want to touch about the recent advancement in MR. Of course, all of you know about a combination, hybrid imaging. We have a MR imaging and the PET imaging. Combinedly, we can also do it. We call it as MR. This gives the anatomical information. This gives the what you call the physiological, functional information. Clubbed together, we call it as a fusion imaging. We do it. You see, this is the MR imaging. We have a PET imaging, and overlay that you can have a fusion, and you can find it out. Beauty of this is once you do a PET, you find the lesion, and that particular area you can do a cross-sectional imaging for better delineation of the soft tissue in MR. That is a great advantage of PET MRI. The same thing here also I have given in the fusion image here. This is another cross-sectional image. Then comes the another advancement is an intraoperative MRI. Of course, it's a wonderful one. IMRI, you know that it refers to an operating room configuration. Basically, it is a MRI incorporated in the operating theater, which will enable the surgeon to make the patient via an MRI scanner while the patient is undergoing the surgery, particularly the brain surgery. It's something like a live. There are two configurations are there in IMRI. The first configuration is patient will be moved to the magnet room to obtain the image. How? See, this is the operation theater. Adjacent room will be a MR room, and you have a sliding door will be there. During the surgery itself, they can transfer the patient to MR. They can do the MRI, find out that, then they can close the surgical stitches can be done. So this is the first configuration. And second configuration, the MRI in itself is a ceiling mounted. It can come from one room to the operation theater itself. This is also possible. So this, of course, this it may be theoretically I am talking, but both the configurations are very expensive. It's not an easy. Of course, you know that this configuration is available in India itself. You know that one institute I can mention, which I have seen physically, is Nimans Bangalore, where they have 3-4 operation theater, and the center they have an MR system. Particularly, Nimans is excellent for the neuroimaging, neurosurgical area. So they have a real advantage. Of course, very expensive. This whole setup comes around 80 to 85 crores actually, because the whole system should be an MR compatible system. That is the main reason why it is costlier. So, and the third advancement is the MR guided focus ultrasound technology. So what do you mean by that? It combines the high intensity focus ultrasound beam and destroys the targeted tissue, particularly the fibroid in the for a gynecological system, no. So that they will be doing ablation type of thing. See, what is the principle here? Here they use an ultrasound with the help of MRI, and they ultrasound. What they do is they use a, you know that in the normal diagnostic ultrasound we use in the range of 2 to 20 megahertz. But in the therapeutic ultrasound, the energy of the ultrasound, what we use something around 4 megahertz, and that is going to be focused to the tumor. See, this is an ultrasound machine. It is getting focused to the fibroid here. And please remember, 4 megahertz is a diagnostic ultrasound, but how it is getting destroyed is, one major difference is the power of the ultrasound. So here we give that ultrasound, what we use in diagnostic is in the milliwatts something, but here we use 1000 to 2000 watts per centimeter square. So the power intensity of the ultrasound, the energy is going to be very high. So that is going to be something like it is going to ablate the tissue. That is called as MR guided focus ultrasound. And the last one, I don't have much knowledge, but little bit whatever I know, I would like to share. MR Linac is being developed to capture the detailed MR images of the tumor and surrounding tissue while the patient receives treatment. It's continuous MR imaging during radiation delivery for gating or tumor tracking. See, what is the instrumentation aspect is, you have a cylindrical 1.5 Tesla. So this is the MR system. Above this, you have a Linac outside the magnet. And here you have a MR parts, which should be transparent to the X-ray beam here. That's how it is designed. And the field sensitive Linac components are located in low field zone. That's very important. Can you see this diagram? Can you see this is the RF cage, where the magnet alone will be inside the RF cage, and the actual accelerator and Linac component will be outside the RF cage. So the RF shield is between the Linac and the MR systems. So that's how it is designed actually. So this is a little bit knowledge I want to throw to you. So that's about the advancement in where the MR is going to be incorporated in the therapeutic aspect also. I think that's the end of my session. So what is the take-home message? We have seen the very important climax of understanding what is the real T2 and T1 and T2 relaxation parameter, which is the parameter responsible for the pattern of intensity in MR image that we should understand, because each tissue has a different relaxation. So that's how we are able to get the different intensity in the image. To get this, we should know about the equipment parameter where we play around, that is TR and TE. I explained you. By using this TR and TE, we are able to get T1 weighted image, T2 weighted image, and proton density weighted image. And little bit we have seen about the recent advancement in MRI. I hope I have done some justification, because it is a vast subject. So I have taken only one component, that is the basic principle of MRI. So any queries or clarification, I'm ready to answer. Whatever I know, I can share it and tell the answer right now. If I myself have some clarification, definitely I'll go through it and put through CMPI, I can answer it also. Thank you very much once again. It's a lovely gathering, and thanks to Dr. Bhatt and Dr. Vel Murugan in particularly for giving this wonderful opportunity to share a little bit about the imaging of MR. Okay, thank you, sir.
Okay. Thank you, Professor Panneer, for your excellent presentation. I hope all the participants will accept and they will join me in this point. Really, you have expressed all the points explained in a very simple way. That's the most of the participant has commented. Given in the chat box.
I'm expecting that I explained nicely. Maybe the diagram image says that 50% might be looking me like this, and maybe 50% maybe like that. I don't know. Hopefully, I take it in a positive way.
Majority of participants have expressed really it's a very nice presentation. However, some of clarifications are there. I'll go through one by one.
Yes, sir.
One Debolina Mukherjee, she want to know for radiotherapy planning with the treatment planning system, which images are best, which either T1 weighted or T2 weighted?
It's a very, very, very big question actually, but I'll try to put it in a different way. Basically, T1 weighted image are good for anatomical information, and T2 weighted image are very good for pathological information. But I told you only T1 and T2 weighted, but there are different sort of images in terms of pulse sequences, which might be totally a different topic. For example, we have a spin echo pulse sequence image. We have a gradient echo pulse sequence image. We have an inversion recovery pulse sequence image. We have a echoplanar imaging. Like that, we have so many types of imaging in MR. There are certain images are good for certain conditions. For example, I want to see an optic nerve pathology. So your optic orbit tumor or optic nerve pathology. For that, the inversion recovery T2 flare, we call it. So that sequence might be better. So like this, we have a various option. It purely depends on the clinical radiologist, which image they say the tumors are seen better. Based on that, we can choose it. And we also can see the what you call the extension of the tumor outline, whether it's a benign or whatever, not only for planning, I'm telling, if it's a benign or a malignancy, how the outline appear, all those details can be get with the different types of accusation also. In accusation also, we have variety of accusation. As I mentioned, different types of pulse sequences are there to get the different type of images. But to put in a simple way, T2 weighted images are good for pathological informations.
Okay, another question is from Sendil Selvan Chellaya. Can you please elaborate about magnet quench?
Magnet quench is actually speaking, there is one is called as, see what happened is, as I said in the beginning, it is a superconducting magnet 1.5 Tesla. It is 30,000 times stronger, means very powerful magnet. By mistake, if they have taken any metallic component, even we have seen a lot of accidents have taken place throughout the world. In India also, a lot of incidents are there. For example, a stretcher has gone. Suppose by mistake they have taken the stretcher inside, it will fly like a projectile and go and hit the magnet system. Suppose if I am going to be in between the magnet and the stretcher, that's all. It is something like a fatal only. So what happens, for example, if something is going to happen, something like that, I want to release, for example, one of the staff got stuck there. How to release? You can't take out the 500 amperes immediately, isn't it? So there is a process called as emergency switch. When you press that, what happened? The superconducting, which holds a huge amount of current, will be removed from that. So what happened? Totally the current will be removed from that. When you remove such a huge amount of current immediately, huge amount of heat is going to be produced, which will boil off the liquid helium inside, and all the liquid helium, see, basically liquid helium will be converted into a helium gas. That helium gas is dangerous actually. 1 liter of helium gas can displace the 8 liters of room oxygen. So you will not know, you will get faint. So now that process is called as quenching. That is suddenly when you switch off the emergency switch for the emergency situation, it is something called as demagnetization of the magnet you are doing. That process is called as quenching. But it is a very expensive process. Once you remove all the helium, once again to make that as a magnetization, and when you want to do the 1.5 Tesla once again, nearly 30-40 lakhs you have lost because of helium. 1 liter of helium comes around 2,000 to 3,000 rupees. And you know that there is an acute shortage in the whole world for liquid helium. So unless it is going to be a real emergency, we should not operate that. So that's about quenching.
Okay, another clarification about quality assurance test. What are the quality assurance tests done in MRI, and how frequently we have to do quality assurance test? These are two clarifications.
Yes, sure, sir, sure. I'll tell that. But to be very frank, my knowledge also in that area is not much, because we have a checklist for that also. We have different quality assurance tests are there. We have an agreement with the company itself, because they have a different phantom and they have their own protocol. We will be physically present, and what they do, only we observe. There are different sort of phantoms are available for that, with the different content, not only water phantom, we have a different content also. For that, we have a different quality assurance test. For example, a simple thing I'll tell you. During the installation, they do something called as field correction, inhomogeneity check. We have a device called as Tesla meter. We have to find out the homogeneity correction inside, and we have to correct it with the help of software, or physically also we can do, which we call it as shimming process. So that is one QA check we do. And second thing is, we also do a lot of check to ensure that T1 and T2 values, what they measure, and with the help of the reference liquids which is given in the phantom, we cross check with that whether that is okay or not. And we also check where there are different types of coils are there which receives the RF signal. That coil tuning aspect, that is electrical and electronic tuning of the coil, has to be done. Like this, we have checked, and normally this is done once in a year only, not so frequently like other tests.
Okay, thank you.
But any problem or issue or any artifact comes in the image related to homogeneity, that we will attend in between also, based on the requirement.
Okay. And another question by Sam Devakumar John Jyoti. What is POST, P-O-S-T, and the 3D Bravo series? That
Post,
we are
I couldn't understand.
What is P-O-S-T, POST?
Post.
Yeah, and 3D Bravo series that we get in MR examination, along with the T1, T2 series.
I'm not very sure about the question. Post and Bravo.
3D Bravo series.
No, it may. What to my knowledge, I think it is something related to the 3D pulse sequence, basically.
Yeah, they are getting in examination, I believe, in my MR examinations.
MR examination, this question.
Yeah, along with the T1, T2 series.
3D Bravo.
Yeah.
See, I'll tell one point in this. Each company developed different types of sequences, and they give acronyms accordingly. They give their own names. For example, I'll tell one sequence. There is something called as fast field echo sequence. This is the term given by what you call Phillips system. Otherwise, we call it as balance FFE sequence, balance fast field echo system. But GE called this as a Fiesta sequence. Siemens are called in some other name. So like this, there is a sequence, 3D Bravo sequence. There's another sequence by a particular brand company. 3D is a volume acquisition. Basically, it's a volume data acquisition. And Bravo, actually, I have to find out to which vendor it belongs. I'm not very sure. Maybe I can get back definitely.
Okay. And if patient is on full bladder, then will it affect the image during pelvic imaging?
See, normally we ask the patient to void and come for any MRI for a simple reason. It is an air-conditioned room. The bladder gets full. The study gets disturbed.
Yes.
So that is one thing we did. Coming to the pelvis, bladder definitely in half an hour, 45 minutes, they are going to do it is going to get filled up only. Doesn't matter. It's not going to be a problem.
Okay. And another two more questions from Mukherjee. What are the advantages and disadvantages of these weighted images? That is one thing.
Advantage and disadvantage of I will tell first advantage and disadvantage of MRI. If you talk about advantage, it has various advantages. For example, I say the soft tissue differentiation. Direct axial, coronal, and sagittal plane can be observed, which you can't do it in CT scan. That is only a reconstruction. But here, direct acquisition of sagittal, coronal, axial plane, or any oblique plane can be done. Disadvantage, of course, it is expensive and time-consuming, all those things. But coming to the advantage and disadvantage of a T1 and T2 weighted image, as I told, each one has their own advantage and disadvantages. T1 is a time is going to be very shorter. But when you go for a T2 weighted, it is going to be a longer time duration. But still, it is going to give a lot of advantage. Why means the pathological information are going to be well appreciated, because in T2 weighted image, I am going to use a parameter called as long TE. What is the advantage of using long TE is the difference between the various tissue in the decay parameter. I am going to well appreciate it. That is the difference between the two tissue are well appreciated. That in our language, we call it as a contrast. Contrast means difference. So that is going to be better in case of a T2 weighted image. So that is going to be a great advantage. Disadvantage means, of course, longer scan time.
Okay. And another question is, this proton density imaging will be useful for treatment planning, radiotherapy treatment planning, or it will be useful for diagnostics?
Yeah, normally for the diagnostic it is used. If at all, particularly proton density weighted images are very good for musculoskeletal system. Musculoskeletal means, for example, joints. Okay. If you are going to treat something in the joints area, even that also can be used. But majority we go for T2 weighted image.
Okay, even that means even for planning, radiotherapy planning also, it will be of much useful.
Yeah. We cannot say it may not be useful, but MSK sometime it can be useful.
Okay. And the last question is, any specific QA for MR Linac as per AERB? Actually, to my knowledge, in India, first MR based Linac is going to come in Hyderabad. I don't think anything, to my knowledge, it is there. Anyway, you are the right person.
I also don't know about the QA for MR Linac AERB protocol. I'm also not sure about that.
Yeah, that's what I also feel. It's the first unit is going to come in Hyderabad. This MR guided Linac. So maybe after some time we may be knowing the protocol.
Yeah, correct.
And is there any? Will there be any interference due to this magnetic field in Linac?
Yeah, that only. It's a very good question. Actually, see, we have the MR machine inside the room, which we call it as RF cage. Okay. That is called as Faraday's cage, we call it.
Okay.
Basically, that cage is made up of a copper shield material. That room construction alone comes around 40 lakhs rupees roughly. With all the 6 sides That is, all the four walls, base, as well as the roof has to be made up of plywood embedded with the copper sheets. Why we use copper sheet is, whatever the signal we collect from the patient is a RF signal, which is very, very weak signal, which we are going to collect it. But you know very well that outside the MRI room, there is a lot of RF sources. For example, CT tube might be there, CT rotating, may be rotating, or any motor may be there, elevators, lift may be there, or any nearby, what you call, other equipments which involves the induction, electrical magnetic induction may be there. That will disturb, isn't it? To avoid that, we have a copper cage. So that copper is going to be a what you call, it is going to be a real filter for not allowing the RF. So it is something like a RF interference is totally avoided with the help of copper material. And of course, what happened during the magnet installation, the homogeneity is done. After doing everything, you should not bring any new metallic component. For example, even the Godrej bureau, you should not keep and bring it and keep near the MR room after doing all the quality assurance tests. Now, what will happen when the bureau comes? That might interfere with the homogeneity. So you may get some artifacts in the image. You will be wondering from where it is coming. So yeah, whatever going to be done during the installation, any new metallic object should not be placed. So this is one important criteria which will disturb the magnetic field homogeneity.
Okay. And another few more questions are there. I think we can continue. Can I?
Yeah, for me, no issues. If I know the answer, I'll tell definitely.
Secretary, sir.
Please, sir, please continue, sir.
Yeah. One thing, sir, you said TR2000, it is donating one particular slice time or whole slice time.
No. TR is basically, it's a RF pulse application gap, basically, between one RF pulse and another RF pulse. Okay. To get one slice, I have to do 256 times like that. Apply RF, switch it off, collect the echo. Apply RF, switch it off, collect the echo. Apply RF, switch it off, collect the echo. I have told only the simple process, apply RF. But there are so many things are there in between one RF and RF also we do. That we will not go now because it might be too much. So like that, I'll be doing 256. When I do 256, how many echoes I am getting? 256 echoes. That if I add up, then I'll get one cross-sectional image. But after collecting one echo, there will be a gap between the next RF pulse. Then why I have to wait for that time? That time I'll be utilizing for the next slice. Like that, it is called as multi-slice acquisition technique will be done. I will not do only 256 and keep quiet for one slice during that time. If I do know for one particular orientation transverse alone, for multi-slice, it will take half an hour. So one MRI scan, it will take 5 hours to complete. So that is not practically possible. So we do something called as multi-slice acquisition simultaneously. Apply RF, collect the echo. Next, I have to apply the RF. In between, I have a gap. And that gap, I'll be doing the next slice. There, I'll be doing first RF pulse and echo. For the next slice, first RF and echo. Like that, I'll be doing simultaneously also.
Okay. And Ranjit would like to know, by using 3 Tesla, how many RF pulses you used? You said for 1.5, you said some 63 something. You'd like to know for 3.
Not 63. Same thing, sir. I have to use 256 even if it is 3 Tesla. No change. Only thing that RF pulse which I am going to apply will be 127.8 megahertz. Frequency will be different. Then only resonance will come, because when I place the patient inside 3 Tesla, the precisional frequency is not going to be 63.9. It is going to be 127.8. So I have to apply RF pulse 127.8. Otherwise, application of the RF pulse 90 degree is going to be same here as well as there. Only the frequency difference.
Okay. What is the advantage of higher Tesla in diagnostic, particularly 7 Tesla?
We have a lot of technical and clinical advantage. Coming to the technical advantage, I'll list out a couple of things, and the clinical couple of things I'll tell you. Technical advantage, the scan time is going to be faster, and I can achieve better homogeneity in 3 Tesla when compared to 1.15 Tesla. So when I achieve better homogeneity, my image quality is going to be much more improved. That is one thing. And second thing is, you know that one of the category what we do is the MR spectroscopy. So when I am going to do MR spectroscopy, when compare 1.5 and 3 Tesla, the peak what I am going to get is going to be a narrow peak in 3 Tesla when compared to 1.5 Tesla, which is going to be broader. So it means that more accuracy, it says. So like that, we have a lot of advantages. And when you go for 3 Tesla, particularly it is going to be very good for a functional MRI. And when you want to do a what you call a functional MRI means, you know that we have something called as dynamic study, perfusion imaging, diffusion imaging, functional MR imaging. Like that, we have a lot of advancement in MR. So those things are going to be better when you go for 3 Tesla. Even 7 Tesla is also available now, but it is you should not go like gimmicks. See, for example, you have a 25,000 good phone. Instead of that, people go for 1,25,000 iPhones. Are they really using everything? That's more important. So we call that as what you call versatility, serves many functions. If you are going to use that, it is going to be definitely good. Otherwise, in 3 Tesla, you have a lot of functions are there. But if you are going to do only a routine job, it is going to be of waste. Definitely, there is a lot of technical and clinical advantage when you go for 3 Tesla. I have listed out few. Similarly, we have more.
Okay.
Even the acquisition time, no, I can acquire very fast. That is the advantage of 3 Tesla.
Okay. And another question from Palani Velu. Is it possible to do plan with the MRI image override with the relative electron density structure?
Yes, it can be done.
Okay,
what is the problem? Because we have an MR image, with that they can do. I think what it means, I don't know, but it can be done.
Okay. Another question, in LINAC MR combination machine, electron therapy, is there any possibility for that?
No, whatever I know, it's mainly for utilizing for this one only, X-rays only. Okay. But electron thing, I don't have much knowledge about that.
Okay.
So whatever I studied in literature, mainly it focus on X-rays.
Okay.
Because electron, the problem is when it enters the magnetic field. I really doubt about that. I'm not expert in that area particularly.
Okay, another question is cooling system. Is it going to be different for MR LINAC? Because already for ordinary LINAC, we have got chiller plant and the deionization.
No, that is going to be same only. See, but it is going only whatever I have studied, the configuration what you make in the MR LINAC above the MR only is that different system. But otherwise, the accelerator functioning, everything is going to be similar only. You should have the cooling system. Yes, definitely not with this one.
Okay,
nothing to do with this.
So it is going to be continue like ordinary LINAC. This is addition to that MR. That cooling system is going to be different.
No, MR cooling is different. It's totally different. That is mainly to achieve the superconduction. That's all.
Yeah, that's what.
For an information, since you have asked, I'll tell you. Actually, the tank, what you see, MR tank is something around 1,500 liters capacity.
Okay.
Each liter is 3,000, 2,500, 3,000. Imagine how much money is inside that. Okay. But acute shortage of helium is there. For your information, for all the people who are listening, now the new MR system has come, which need only 1 liter of helium. That's all. Only 1 liter of helium. It yet to come in India. It will take long time. Purely commercial aspect, economy aspect is concerned. But now the new, for example, recently I have witnessed the Siemens equipment with that. It is only 1.9 liters of liquid helium. That's all.
Okay. Another last question. If increase number of slice, TR also increases. What is the reason behind that?
Yes. Because I want to accommodate, see, in the particular one TR, I can do from 5 to 6 slice. I told you know the gap, whatever possible only I can do.
Yeah.
Suppose if I want to do more slice, then what will happen? The TR will be doubled. To avoid that, I can extend the TR to some extent so that I can accommodate the slice. For example, within one RF pulse and other RF pulse, that is a TR, I can do 5 slices. If I want 8 slices, what I have to do? another TR I have to use for another 3 tests, but that will double the time. But instead of that, if I extend the TR, instead of 300, I can make it 500, then I can accommodate the 8 slice. But please remember, you cannot extend more than 700, 800. If you go 1000, I want to accommodate all the slice, then it is not real T1 weighted image. You are going towards the proton density.
Okay.
So that point you have to remember. The TR
Okay.
also, I have mentioned the upper limit also, that you should not cross.
Okay. One final, that last question.
Okay.
I think Kirtana would like to know any side effects, that's biological disadvantages when a person undergoes MRI. Is there any side effects?
Internationally, as far as I know, I myself in the field for nearly, if I am correct, 32 years, no literature says there is a bioeffects of magnetic field. Okay. Only one thing we take a precaution is when we do a fetal MRI, that is a pregnant ladies.
Okay.
That also no literature says, but still we try to avoid first trimester of the pregnancy. We do for second and third, but even the literature says that you can do for first trimester because no side effects have been proven so far. No bioeffects as far as the magnetic field, but there are some. When you apply the RF, no, that RF has some effects. Thermal effects are there.
Some tingling sensation.
Tingling, all those things are there.
Okay.
Some people developed blisters also. If the RF energy is not properly planned, then they can develop some blisters. That is possible. That is possible.
Yes.
There is one more thing is there, which I am not touching now. That is something called as gradient field.
Okay.
That I can touch only if I am able to do it a separate thing on MR instrumentation. Okay. That is called as variable magnetic field. We call it as time varying magnetic field. That has some effect. And not much, but it has some bioeffects.
Okay. So with this, I would like to conclude. Sir, really, it's an excellent, very informative talk. Many people have appreciated. It's a very simple way you explained. It's really benefited so many people, and I don't think it's going to stop with this. As I told, the first unit MR guided LINAC is going to come in shortly in Hyderabad. Once if it comes, much more doubts and clarification may be required. So we may have to get some more lectures on this topic. I hope we'll get your support. With this, I join CMPI in expressing sincere thanks for taking your time in giving a lecture in CMPI Monthly Web Lecture Series. Thank you, sir.
Thank you, Dr. Velmurugan and Dr. Bhatt once again for a wonderful opportunity, and hope the audience would have enjoyed. Physicists would have enjoyed this program. Thank you.
Yes,
thank you.
Yes. Thank you. Thank you, sir.
Thank you.
And thank to
Dr. Bhatt, please.
Dr. Panneer sir for informative and wonderful presentation on MRI and its clinical application. Thank to all participants, and see you next month on the 4th Friday at same time, 7 to 8, with a new topic. Thank you to all.
Thank you.
Thank you, sir. Thank you.
Thank you.
Thank you. Dr. Bhatt.
Yes, sir.
Okay, thank you, Dr. Bhatt.
Thank you, sir.
Okay. Thank you. We'll see you next month.
Thank you, sir. Thank you.
Bye.
Bye.